Boa tarde a todos. Vamos hoje dar início a mais um seminário aqui no canal do Programa de Pós-Graduação em Química da Universidade Federal Fluminense. Agradeço a todos vocês aí pela presença e aproveitem aí para conhecer o nosso conteúdo no canal e aproveitem também para se inscrever no mesmo. Hoje nós temos aqui o prazer de receber o professor Leonardo Alvarez para fazer uma apresentação sobre o seu trabalho e convido aqui o professor Eduardo Ponzio para as devidas apresentações. Boa tarde, Eduardo.
Boa tarde, David. Boa tarde a todos que estão conectados e um olá para todo mundo que assista depois a palestra. Então, é uma honra para mim apresentar o professor Leonardo. O professor Leonardo, eu tenho uma parceria já de longa data. O professor se formou em Química, bacharelado em Química Orgânica pela Universidade de Costa Rica. Depois da formação em Química, ele trabalhou numa indústria química que se chama Indústria Química Costarricense durante 7 anos, onde adquiriu uma grande experiência em sínteses orgânicas a grande escala de feromonas para o controle integral de pragas e desenvolvimento de agroquímicos e produtos veterinários. Depois desses 7 anos, ele decidiu voltar à vida acadêmica e aí ele viajou para a Europa, onde foi para a Universidade de Lyon, onde fez a maestria em catálise homogênea. E depois ele se mudou e foi para Grenoble. Ele fez o doutorado na Universidade de Grenoble em síntese e catálise assimétrica. Ele fez 2 pós-doutorados, um pós-doutorado em catálise heterogênea na Universidade de Lyon e um segundo pós-doutorado em catálise homogênea no Instituto Catalán de Investigações Químicas, na Espanha. Depois disso, voltou para Costa Rica. Hoje é professor associado da Escola de Química da Universidade da Costa Rica, onde desenvolve sínteses químicas aplicando os conceitos de química verde. É autor e coautor de vários artigos, especificamente em síntese de química orgânica, catálises, tem livros publicados, tem patentes, e tem várias colaborações com diferentes universidades, especialmente com a França, Estados Unidos e com a gente aqui na UF. Então, Leo, seja bem-vindo e muito obrigado por aceitar o convite de apresentar o seminário. Bem-vindo, Leonardo.
Thank you, Eduardo. Muchas gracias, and thank you. Actually, it's a pleasure to be here with you. It's always an honor to participate in this kind of activities, and it's always a pleasure to share with you guys at the UFI. All right, so I'm really honored, and thank you all for watching this. All right, so the seminar that I would like to actually share with you today is entitled Deep Eutectic Solvents in Organic Synthesis. All right, but before starting the seminar, I will kind of like to put you a little bit into context. All right, remember that after green chemistry was born, that was like early in the 1990s. All right, I don't know if you remember Paul Anastas, who is one of the top chiefs of the Environmental Protection Agency from the United States. Well, Paul Anastas, he developed all the concepts of green chemistry, and since then, we, the chemists, we have been trying to develop and to find out new ways of doing chemistry. All right, especially like new reaction conditions and new chemicals that are not toxic, not only for human beings, but for the environment as well. All right. So among everything that has been done, you cannot actually leave behind the, let's say it's kind of the quest for the Holy Grail, but in this case is the quest for new alternative reaction media, okay? And there's a lot of work that has been done in that subject, especially in what now it's known as green solvents, all right? And talking about green solvents, well, in this case, I would like to present you these kind of deep eutectic solvents, okay? And especially some of their applications and some of the experiences we have had in here in Costa Rica while having fun doing green chemistry, all right? So just to start, well, let's give a little definition about what green solvents, what deep eutectic solvents are. And from now on, I will refer to them only as DES because it's shorter, all right? So a deep eutectic solvent is actually a mixture, okay? It's a mixture of two components or even more, but let's start with a simple definition, okay? Just two components, okay? That whenever they are mixed in a specific proportion, all right? You will have, as a result, you have a mixture that has a huge depression in the melting point, all right? And by consequence, you will get a liquid, all right? So that's what is known, or that's how it's defined, an eutectic mixture. So the thing is, if you can see from this graph in here, the thing is you take two, let's say two solids, and that's the great thing of this, because you can make liquids from solids, all right? And then you're gonna start mixing them. Remember from physical chemistry courses, all right, that whenever you mix a solid, actually there's gonna have because of the colligative properties, you're gonna have a decrease in the melting point of it. So the idea is to mix two solvents, or two solids, sorry, and then you will see that the melting point is going to decrease, okay? And then the goal is to reach a specific proportion on which you will have the lowest.
Sorry, Professor.
See,
I think there is a problem with the PowerPoint because we are not watching.
Oh, yeah.
Presentation.
Okay, let me see. Jesus. Okay, let me see how. Let me see. Let me start again.
No problem.
I don't know if the problem is solved right now. No, not yet.
No.
Let me start again. Do it again. Just 1 second. Let me see if I can solve this. Jesus. All right. Slow. Wait. I think now it's working. It should be working. Oh, Jesus. Wait, these froze. Just 1 second, please. I'm trying to solve the situation. It's just everything froze. I don't know why. Direction computers. Let me. Problem is the computer is slow. That's the thing. All right, there. And then can I start it? All right. I hope you're seeing the PowerPoint. Is it solved?
Yes, we can see.
All right, perfect. All right, so thanks a lot, and I'm really sorry for that. So as I was saying, okay, deep eutectic solvents, all right, they actually are a mixture of two components, all right, and actually the idea is to mix two solids, all right, and because of the colligative properties of mixtures, all right, whenever you mix a couple of things, you will have a depression either in boiling point or in melting point. So in this case, what I was trying to explain is that, for example, the idea in this case is that you will combine two solids, all right, and the every time that you do that, there's always going to be a depression in the melting point, all right, of that mixture. So the goal here is to reach a specific proportion where the depression on melting point is the highest, all right? That point is known as an eutectic point, all right? So whenever you have mixtures that are prepared this way, well, they have some interesting characteristics, like, for example, we can actually say that they are non-flammable, they have very low vapor pressures, okay? They are stable against air and moisture. And this is a very important characteristic, because what happens is that depending on what kind of solvent you have, like, for example, when you live in a tropical country like here in Costa Rica, like, relative humidity is really high, and I know that in Rio it's really high as well. So whenever you want to have, let's say, anhydrous solvents, this is difficult, all right? So you have to do a lot of things, a lot of work in order to avoid your solvents from getting wet, all right? So these solvents are stable against air, stable against moisture, okay? They are really nice solvents. There are a lot of different compounds that can be dissolved in this kind of solvents, all right? They also are chemically stable. Yeah, we can talk about that later. They are almost inert, all right? And the other thing that makes them wonderful is that the components, they have probably from 0 to very, very low toxicities for the environment. So, okay, this is a great thing, especially if you're trying to make green chemistry, all right? The other thing is that the starting materials are, or could be, cheap, all right? And the other thing is that they are very, very, very easy to prepare, all right? And actually, the simplest method for preparing this kind of mixtures is actually you take two solids, you mix them, you heat them up a little bit, and then voila, you have a liquid. Okay, you have your solvent. So as you can see, we have several characteristics, and probably that's the reason why they have been proposed as alternatives for organic synthesis. All right, so that's the main idea. All right, and if we want to talk a little bit about their history, okay, well, actually everything starts with this guy here. This is Professor Andrew Abbott. Andrew is a professor of physical chemistry at the University of Leicester in the United Kingdom. All right, and back in 2001, he published this small communication back then, but actually they reported low melting mixtures of ammonium salts with Lewis acid. Okay, he used like zinc chloride, aluminum chloride. All right, and the thing was that these mixtures were liquid or are actually liquid at room temperature. All right, a couple of years later, in 2003, he reported actually the substitution of those Lewis acids with an organic compound, in this case, urea. All right, so and at that moment, Professor Abbott, he said, okay, whenever you have a specific kind of compounds that you mix, and back then what he was reporting was that you will always get and DES, whenever you combine or do a complexation of an ammonium salt with either a Lewis acid, okay, and for example, in this case, he reported these three ammonium compounds, and he said whenever you mix one of these ammonium compounds with a Lewis acid like zinc chloride, magnesium chloride, or manganese chloride, all right, you will get an eutectic mixture, all right, and the huge advantage of their later work was that they were able to replace, you know, these Lewis acids with hydrogen bond donor compounds like this one. So here you have like 7 possible compounds that you can mix in different proportions.
Leo.
Yes.
Profesor Leonardo. La presentación está parada. Lo que vamos a hacer, vamos a interrumpir. Pessoal, vamos interromper a live só um minuto para ver o que está acontecendo e voltamos. Pode ser?
Sim, 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 sim. Déjame ponerme los anteojos.
Todavía seguimos en la live. No, el problema es cuando le pones modo de presentación no se ve. Lo mejor es ir cambiando, cuando vayas hablando, anda cambiando slide por slide con el mouse.
Ok, pero entonces es que necesito... Ok, voy a parar la screen. Ok. Ya, lo logré. Es que no podía cambiar las... Ok, vamos a ver. Ahí. Y entonces puedo hacer una cosa. Quito esto. Quito esto. Ahí.
Sí, y ahí lo mejor es ir acompañando vos, que va cambiando, porque de la otra forma no se queda congelada en un slide.
No hay problema. Perfecto.
Ok, ¿podemos seguir aquí entonces?
Sí, claro.
Bueno, muchas gracias. Perdón por la interrupción.
No te preocupes. Okay, well, sorry again for the interruption. And what I was saying is that Professor Abbott, well, he discovered that, for example, whenever you mixed quaternary ammonium salts, okay, like the ones I'm showing in here, okay, sorry for the size, but the ones that I'm showing in here with either Lewis acid like zinc chloride or manganese chloride or aluminum chloride, okay, you will get a deep eutectic solvents. Or instead of that, the other improvement that they reported was the replacement of those Lewis acids with these compounds that actually they act as hydrogen bond donors. All right. So now you can actually ask yourself, okay, I understand we have a mixture of 2 compounds, but what's going on? What's actually causing the depression and melting point? All right. And actually, Professor Abbott, he kind of stated an hypothesis, and he explained that the depression in the melting points was caused by the charge delocalization that's going to take place whenever the halide ion that form parts of your quaternary ammonium salt, okay, actually is surrounded by the hydrogen bond donor, okay, and that thing is going that situation is going to actually make a delocalization in charge, and that actually is what's going to cause the depression in melting point. All right, so this is what he stated as an hypothesis. Right now, this explanation is still accepted. All right, and whenever you read, let's say a paper, a recent paper on this subject, they're still using the same hypothesis. All right, so there's still a little bit of work that needs to be done in this subject in order to test if this hypothesis is true or not. All right, but well, in conclusion, all right. Deep eutectic solvents. Deep eutectic solvents are going to be. A mixture, okay, of two things, of two compounds. All right, and the thing is that when you mix them in a specific proportion, okay, the melting point of the resulting mixture is going to be lower than the melting point of the individual components. All right. And this phenomenon is not as weird as you may think, because in real life, we have honey. I know that almost everyone probably here has seen, smelled, tasted, and eaten honey. All right. Well, honey is an eutectic system that is formed by the combination of solid sugars. All right. And whenever those sugars are combined in a specific proportion, well, that mixture is going to melt. So honey is an example of this kind of systems. All right. And right now, the term DES actually is being applied in a broader context. And by that, I mean, it's just like right now, they're using the term DES to any possible combination of two solids or two compounds that after mixing, they will form a liquid mixture at room temperature, okay? It doesn't matter if you have reached the eutectic point, all right? If it's just liquid, right now, you can say that you have a DES, and even though it's not that deepest, all right? And because of that, okay, actually now we find in the literature different acronyms that are used for referring to other possibilities. For example, NADES. Now those are the natural deep eutectic solvents that are formed by the combination of natural products. All right. Or we have the THEDES, the TEDES. Okay, those are the therapeutic deep eutectic solvents. All right. And as an example in here, the thing is, whenever you mix one of these terpenic compounds that we have in here, cineol, cymene, limonene, stuff like that, okay, or menthol, or even menthol, with a drug like ibuprofen, you will have an eutectic system, all right? And the thing is that because you're going to have a liquid, all right, you can dissolve a drug, and you can use this mixture as a vehicle in order to develop a pharmaceutical formulation. All right. So yeah, those are kind of examples of the possibilities that we can find whenever using deep eutectic solvents. All right. So to our day, there have been reported 4 different types of deep eutectic solvents. All right. The type 1 was like the first that were reported by Professor Abbott. Okay. Professor Abbott, what said was that actually he reported the combination of an ammonium, a phosphonium, or a sulfonium salt with a Lewis acid. All right, those are type number 1. Type number 2 actually are the ones that are formed with the same organic salt, ammonium, phosphonium, or sulfonium. Okay, but in this case, they're going to be mixed with a Lewis acid that it is hydrated. Okay, so this opens the opportunity of using, let's say, hydrated iron chloride, hydrated copper chloride, and stuff like that. Type number 3, okay, are the type of DOSs that he reported back in 2003, that actually they are formed by the mixture or the combination of ammonium, phosphonium, or sulfonium ions with and in this case with a hydrogen bond donor. Okay, and type number 4 are the ones that are formed using an inorganic cation, okay, with an hydrogen bond donor. Okay, well, in this seminar, I will talk only about type number 3 because actually those are the deep eutectic solvents that have been used the most in literature. All right, so there are more examples of the applications of DOS of the type number 3. So that's the reason why I will talk to you about them a little bit more. All right. So, well, now let's talk about some applications of these solvents. And let me start with an example in metal processing. All right. As you know, traditional metal processing actually uses aqueous solutions. All right. And this is normal because in water, you have high solubility of your electrolytes and you will have like high solubility of your metal salts. All right. So water, it's the solvent of choice. The problem with water, remember that water has a very, very narrow potential window. Okay. And that gives us like a small or very, very poor current efficiencies, and actually it's hard to get good yields from the fact of using water. Okay, and you have to remember that when you're using water, there's always going to be the production of hydrogen. All right, that's the problem. Okay, and with the production of hydrogen, you will have what is called the hydrogen-induced cracking of your substrate. All right. Well, luckily enough, DOS, they are able to solubilize some metal oxides. So actually they can be used as solvents. Okay. And right now you can find 3 different solvents that are commercially available. All right. And for example, you can have glycerin, ethylene, Relene. Then those are TOSs that are based on choline chloride. Okay, and for example, glycerin is choline chloride mixed with glycerin. Ethylene is choline chloride mixed with ethylene glycol, and Relene is choline chloride mixed with urea. All right, and in parentheses here, I'm showing you, I'm giving you the proportion that you need to mix. These are molar proportions. All right. And whenever they have been used in metal processing, all right, and you compare the results to the results that you get from using water, okay, you'll have some advantages. Like, for example, these solvents, they have a wider potential window, all right, and the current efficiencies are a little bit higher, especially when compared with polar organic solvents. Of course, it's not going to be higher than water, but it's higher than when you use organic solvents. All right, and because there's no water, there's no hydrogen produced. All right, so you have a lot of advantages, and right now, from what I know, this is a very important fact, a very important subject to develop. There's a lot of funding in Europe actually that it's been offered to researchers that would like to develop these any kind of investigation in this area. All right. Now, I would like to talk to you or to present to you about the applications of deep eutectic solvents in extraction technology and extraction tech. All right. Actually, one of the major advantages of these compounds is that of these solvents is that actually you can tailor them. You can modify, you can look for a specific combination of components in order to get a particular polarity. All right. And right now there have been reports of combination of compounds that have given rise to hydrophobic eutectic systems. Okay. Like, for example, whenever you combine menthol with carboxylic acid like lauric, lactic, or even citric acid, you'll get an eutectic system. All right. For example, whenever you use quaternary ammonium salt, okay, and you mix it with a carboxylic acid like decanoic acid, all right, you will have an hydrophobic eutectic mixture. Okay, and well, choline chloride as well. Whenever you mix it with chlorophenol, you have systems like this showing in the picture, where you can actually see that there are 2 phases. All right. Well, these kind of combinations, they have the advantage that they can be used in normal extraction applications. And one of the examples that I brought you here is the removal of sulfur compounds from fuels. All right. And what happened here is that this group, what they did is just like they simulated a liquid fuel. Okay. They were using normal octane, because it's going to be similar to gasoline. All right. And they prepare solutions of thiophene, benzothiophene, dibenzothiophene, all right, in that liquid, in that solvent, all right. And then they perform an extraction, okay, with a hydrophobic eutectic solvent, all right. And here are the results. Actually, whenever they did the mixture, all right, and they made the extraction in just one shot, all right. As you can see, the removal of each one of the sulfur-containing compounds just after the first extraction, actually, they were able to remove more than 70% of each one of them, all right? And by repeating cycles after the third cycle, only like less than 2% was left inside, all right? So yeah, nice, isn't it? You can remove sulfur-containing compounds. As you know, like... trying to do this with regular extractions, it's difficult. Actually, you have to use heavy metals to complex your sulfur compounds in order to get really nice extractions. So in this case, actually, the use of this kind of solvents is going to avoid you the use of that kind of systems. All right, and you will get like nice results. All right, and another example that I would like to share with you is the use of these kind of solvents in order to extract metal solutions. Okay, and in this case, the authors, what they did, they prepared, let's say, concentrated solutions of transition metal salts. And what they did is just like they prepared like a concentrated solution of cobalt chloride in water. Okay, and they extracted with a deep eutectic solvent that it's formed between the decanoic acid and lidocaine, all right? And actually, they were able to perform the extraction at room temperature. And as you can see here in the picture, the first tube is just the solvent, all right? The tube in the middle is the aqueous solution of cobalt ions. And then the third tube, okay, is what resulted from the experiment. Okay, and as you can see, it's kind of obvious, that from the pink coloration that is caused by the presence of cobalt ions, it moved from the bottom, that it's the water phase, to the top, that it's the organic phase. All right, and they said that actually nearly 100% of the cobalt ions were removed, and that this system works not only with cobalt but also works with other metals like nickel, zinc, copper. All right, so it's amazing, no? You can make an extraction of an inorganic salt using organic compounds, all right? Something you wouldn't expect to take place, all right? Another example that's actually even I find it even more fascinating is that this other group, they did kind of something similar, but in this case, okay, they first tested the solubility of some transition metal sulfates, okay, in this kind of hydrophobic eutectic, all right, and they used thymol and capric acid, okay, as a solvent. And what they did is just like they prepare like individual samples of transition metal sulfates, and in here, as you can see, they were able to perform some extraction in some cases, like for example, chromium. Well, they found out that chromium prefers to stay in the water phase, but manganese, it goes up. Okay, iron 3, iron 2. Well, you see, there's some partition actually going on, and some of the ions are going to the organic phase. Well, cobalt and nickel in here, they prefer the water phase. And in the case of copper, well, there's a partial removal. All right, and as I said before, okay, but because in here in this example, you see that cobalt stayed in water, and in the example that I showed you just a couple of seconds ago, cobalt moved to the organic phase. Well, it happens because you can actually do that selectively. All right, you can modify your system in order to have this kind of behavior. All right. So the amazing thing is that then after they tested this, they prepared a mixture of those sulfates in water. Okay. And then they performed the extraction of that aqueous mixture. Okay. And they performed the extraction, and they were able to actually to separate some of the ions were moved to the organic phase and some others stayed on water. Okay. So this is amazing. As you can imagine, well, you can tailor your solvent in order to perform selective extractions, all right? And you might, for example, if you have a mixture of heavy metals that are polluting, let's say water, okay, you can probably develop a system that might extract heavy metals and leave the others that are unharmful, will leave them behind in water, all right? So this is really a huge discovery, and actually a very nice application of these solvents. All right. Well, now let me talk you about a little bit about the application of these eutectic systems as reaction media. Actually, that's the title of the seminar. All right. And as I said before, I think Relin is one of the mostly used DOSs. Okay, and remember that Relin is formed by the combination of urea and choline chloride. All right, choline chloride has the advantage that it's economic, it degrades really easily, is non-toxic, and you can even eat it. All right, so yeah, there's no problem with choline chloride. And whenever you need to produce huge amounts of choline chloride, well, choline chloride actually is prepared by the Johnson-Matthey process, okay, and that's a gas phase reaction. This is just one step. Actually, what happens is just a condensation reaction between trimethylamine, ethylene oxide, and hydrogen chloride. You're going to get like choline chloride as the only product, so the atom economy of this reaction is 100%. And the environmental factor of this reaction as well is nearly zero. So yeah, you get a lot of advantages in using this process. And remember that not only choline chloride, but choline itself, actually, choline is one of the products for protein metabolism, all right? And it is also the starting material for the synthesis of acetylcholine chloride. And this compound is really important in brain chemistry, all right? So, well, in one side, we have choline chloride that has all these advantages. And on the other side, we can talk a little bit about urea. Urea is also cheap and is really commercially available. It's completely non-toxic, all right? It is prepared using the Bosch-Meiser process. That's another condensation gas phase at 200 degrees, 300 degrees actually. You condensate ammonia with carbon dioxide, all right, and then you get urea. Another 100% atom economy reaction with almost zero waste, so with an environmental factor of 0, all right? And remember that actually urea is produced in our kidneys and in our liver, and it's eliminated by our kidneys. So actually it's a non-toxic chemical. So the advantage of these two chemicals is that because they're not toxic separately, all right? So you can imagine that you can easily transport huge amounts of these compounds without any restrictions or with a little restrictions, and then you only have to mix them and you'll get your solvent, all right? So, and because each one of these components is not toxic, you will expect that your solvent or your combination is not toxic as well, all right? So yeah, that's the reason why, or probably the explanations why Relin has been used a lot, all right, as a solvent in organic chemistry. All right, and here are some of the examples from the literature that I would like to share with you. And for example, Relin has been used in the alkylation of aromatic primary amines, all right? And in here, as you can see, we have, let's say, electron-rich and some electron-poor anilines. And they were able to be alkylated in Relin at a not so high temperature, 50 degrees, all right? And the thing is that this system has the advantage of you can perform N-alkylations, all right? The formation of the dialkylated product, as the author says, is almost zero, or actually they didn't find anything. And well, they were able to recover the solvent and reuse it several times. Yeah, and just these little characteristics, these little properties of the application of this system actually is an advantage. Like, for example, if you would ask me how to do that, all right, I will tell you, well, you're going to grab your aniline and then you're going to dissolve it in THF, anhydrous THF, all right? So you have to treat it to be anhydrous. And then I will probably tell you to drop down the temperature to -78, all right? Use a very strong base like, I don't know, LDA or stuff like that. Okay, and still at -78 degrees, I will tell you, okay, now you're going to add slowly the alkyl halide, all right? And you have to be very careful with the temperature, because the temperature starts to rise, then you'll have probably elimination reactions, all right? So you'll have undesirable reactions, okay? And even at low temperature, okay? Well, using Relin, you don't have those problems, all right? So actually, yeah, you get rid of all those problems. So the application of this system gives you some advantages, all right? Well, a second example that I brought you is the oxidation of benzyl alcohols, all right? Well, the authors were able to perform the oxidation of benzyl alcohols, and actually is a mild oxidation because they isolated the aldehyde. And let me tell you, even though this transformation seems to be easy, all right, well, if you're doing green chemistry, actually this is a really difficult transformation, because if you don't want to produce a lot of chemical waste or toxic waste, well, actually this transformation becomes really, really tough. All right, I can tell you that by my own experience. All right, so in this case, they were able to oxidize not only electron poor, but also electron rich benzyl alcohols. All right, and without the formation of any undesirable product. There were no carboxylic acid formed. There were no brominated compounds formed. All right, and another advantage is that they were able to perform oxidations selectively. Well, as you can see, they're using NBS, that it's a radical area oxidant. All right, so reaction will take place through a single radical mechanism. All right, and if you know that, you can take an advantage of the system, because actually they were able to perform a selective oxidation of a secondary alcohol in presence of a primary. All right, so inverting the reactivity of the functional groups, because we already know what kind of mechanism we have. All right, and then they also made it, even though it was expected, when they switched the solvent to a regular organic solvent, well, they reported that their yields at the end of the reaction started to decrease. All right, so that's the thing. Well, we can make a tough transformation at a not so high temperature and still get nice results. All right. Well, another example that I will love to share with you is this one. Okay, the reductive amination of, in this case, aromatic aldehydes or ketones, because they use a couple of ketones there. Okay, and in this case, Relin wasn't used as a solvent. All right, as you can see, it was used as a catalyst. All right, and they did that because at the beginning they tried to use Relin as a solvent, but they found out that actually sodium borohydride is not soluble. Okay, so they had to use methanol as a solvent. Okay, and to do that, they were able to actually dissolve everything in methanol and just add a little bit of Relin, and they found out the reaction was faster, was even faster without the use of Relin. And so they were able to perform this transformation without any other catalyst. And the thing is that, as you can see, they are making a multi-component reaction, all right? And this is not really easy because of all of the possible reaction pathways that you may have whenever you combine several molecules, all right? And yeah, if you want to do it in a classic way, and this is how we used to do it in our lab, to do this, to prepare this kind of secondary amines, first, what you need to do is just like prepare your Schiff base by the condensation of your aldehyde with the amine first, and then isolate that, all right? And after that, you will do the reduction step, all right? And in this case, you won't be able to use sodium borohydride. You will need another oxidant like sodium cyanoborohydride that actually is kind of toxic because it's got cyanide on it, all right? Well, the thing here is that, okay, they're using a small amount of relin just as a catalyst to activate the formation of the Schiff base, and that in the same reaction, at the same time, once the imine is formed, well, is reduced, all right? So they are able to do this just in one pot, all right? So that's a huge advance, you know. This is a really nice result because you are reducing the manipulations of your chemicals. So as you can see, well, relin, or actually not only relin because there are some other combinations, but deep eutectic solvents, they actually can be used either as solvents or can be used as catalysts, as I showed you here in this slide, all right? And yeah, so the results are so far encouraging, and actually that's what actually not force us but move us to try this kind of chemistry, all right? And right now I will gladly share with you some of our experiences using these solvents, all right? So I will talk a little bit about Costa Rican applications of these mixtures, all right? And everything started a couple of years ago, okay? Back then, I had a graduate student who was working on the synthesis of, of molecular organic wires, yeah? And to do that, she needed to prepare several grams of this compound, all right, of this acetylenic alcohol, all right? And well, to do that, well, she improved a system, classic Sono-Gashira Copeland system, all right? And she used THF and triethylamine, all right? And using that system, she was able to get nice results, okay, on a 1 gram scale reaction. But the thing was that she needed to produce like 15 grams of that compound, all right? So what I told her, well, it doesn't matter. You need the compound, well, make the reaction several times until you get enough. And she did it, all right? But later, because it's so kind of a lot of work to do, to repeat 20 times the same reaction. So we started looking for another approach, and we found out that actually using relin as solvent, we were able to get our compound. Okay, the yield decreased a little bit, okay, but the thing was that using relin, we were able to scale up, and the reaction was, we were able to perform the reaction in order to obtain 15 grams just in one shot, all right? And we decided to do that because in that case, we weren't in the need of using THF. Remember that THF, to make this kind of chemistry, you need to dry it. You need to get rid of oxygen and all that stuff. You need to really handle it under anhydrous and inert atmospheric conditions, all right? The same with triethylamine. Well, using relin, the only thing that we needed to add was just a couple of drops of triethylamine, because remember that in a Sono-Gashira couplet like this one, triethylamine actually acts as a reducing agent for palladium, all right? Using these new conditions, we are able now to produce these 4 alcohols that I'm showing in here. The parentheses are actually the isolated yields whenever you make the reaction using relin, all right? Well, as you can see, yields stay nearly the same. And the advantage is that we can make the reaction at a very higher scale, all right? Saving us time and saving us even money, all right? The second example is about the synthesis of fluorescent chalcones, all right? Well, this synthesis involves Claisen-Schmidt condensation of just an aromatic aldehyde with an acetophenone, all right? And firstly, what we did, because, we are always trying to make synthesis in a green way, we optimize the classic conditions, all right? So we firstly used a mixture of ethanol and water, all right? And then we tested the conditions until we reached the minimum amount of solvent that was needed in order to get a nice yield. But to do that, the sacrifice was that we needed to use an excess of base. Well, even with that, after a couple of days at room temperature, we were able to isolate the compounds in nice yields and with high purity, all right? But now, if we use Relin instead of that combination of ethanol and water, we only need to use a small amount of base, all right? The yields stay nearly the same, but the thing is that reaction is faster, all right? And if before we needed like a week or so to have 3 compounds, okay, right now we can have 3 or more compounds in the same week, all right, because reaction times are faster, all right? Well, this is the work of one of my actual undergrad students, and hopefully she will be able to defend her thesis early next year, all right? And the last example that I would like to share with you involves the synthesis of triazoles. A couple of years ago, I started working in cooperation with Professor Poncio from the UFF, all right, and we were in the need of producing this triazole, all right, this benzylphenyl triazole, okay. And back then, what we used to do is to prepare that compound in a 2-step reaction sequence, okay, where the first involved just an SN2 substitution, but we needed to use DMF, all right. And remember that DMF is not a very good solvent concerning the environment, all right? It actually is really toxic, not only for environment, but for human beings as well. So yeah, but it was the combination of solvents that worked back then, all right? And even though we were able to get our product in it's about like a 90% yield overall, the other problem was that we needed to handle this benzyl azide, all right? And I don't know if you're aware of, but organic azides are explosives. Yeah, we really needed to handle this compound with care, regulating the temperature very well, and actually trying to avoid any strong movements. Yeah, because we were in the risk of explosion. Luckily, we didn't have any. And to our delight, right now, we can perform the synthesis of that compound, of the triazole, as a multi-component reaction, all right? We start with the same starting material, but in this case, we just put everything in the flask and wait for a couple of hours, and then we are able to isolate our target, our desired product, but in a higher yield, all right? So yes, this new methodology avoids us the use of DMF and avoids us the handling of any explosive things, all right? And we have been able to prepare these other 3 compounds at a very nice scale. And well, they are waiting in line in order to be shipped to Brazil. Probably in the next future, they'll be tested at Professor Leonardo's lab, all right, as a corrosion inhibitors, all right? And yes, well, before finishing, I would like to comment you something about the recycling of these solvents, because as I have mentioned, some of the authors actually they recycle the DOSs because actually it is possible, all right? But I would really like to give you a comment on that subject, because whenever you make a reaction using a DOS as a solvent, the usual workup is to, when the reaction is over, you quench it with water, okay? And then if you're lucky enough, your organic is going to separate and then you'll filtrate and that's all. But sometimes it doesn't. And sometimes you have to perform an extraction using ethyl acetate or dichloromethane, stuff like that. And then when you evaporate that, you get your mixture, but your product. But that kind of operation is going to leave you with an aqueous solution of your DOS. All right. So if you want to recover your DOS from that, you need to perform a couple of washings with a non-miscible organic solvent. All right. And that, in order to get rid of any remaining chemicals that are in the DOS. All right. And after that, you need to evaporate water under vacuum. All right. Once you do that, your DOS actually can be reused. Okay. But the thing is that there's always the need of very huge amount of energy. Evaporating water, even under vacuum, actually uses a lot of energy. Okay, it is not worth it. So what I'm doing right now is actually I'm encouraging my students to develop a critical thinking. All right, and actually what I ask them is to really analyze if it's really worth it or not to perform a recycling, okay, of the solvent, because as I showed you before, the components are non-toxic. So well, you can dispose it as a non-toxic waste. All right, and what we do actually is that whenever we're making, let's say for example, when we're doing catalysis, that you're testing reaction conditions, we use a fresh batch of solvent. All right, just to avoid or to reduce the number of unknowns, and yeah, we save it. Okay, and when we have enough, all right, we decide if it's worth it or not to recycle it. Okay, that's the thing that I would like to comment on that subject. Actually, the idea is to try to develop a critical thinking, all right, on the subject, and then make an analysis and decide whether you recycle or not. All right, and just to conclude, well, as you can see, DOS solvents, they are good alternatives for replacement for volatile organic compounds. All right, and they have huge applications going from metal processing to electropolishing, electrodeposition, the removal of sulfur compounds from fuels, the metal extraction technology, or even reaction media. And if you use them in organic synthesis, this is actually a very huge improvement. All right, a very big improvement in green chemistry. All right, especially if the components, they come from renewable sources, if they're biodegradable, if they're non-toxic. Yeah, this is really a huge improvement in green organic chemistry. All right, and as you have seen, they are versatile. They are compatible with a lot of reaction conditions, ranging from acids, strong bases, metals, oxidants, reductants, stuff like that. But even though they work, as I've shown you, they work, there's still a lot of things that have to be studied. Like, for example, we are still using the hypothesis of Professor Alvarez and explaining everything by the idea of that everything is being stabilized or activated by hydrogen bonding. But that there's a lot of other things going on, and I think that it's worth it to give it a shot and take a look more closely to see what's going on. All right, and to finish, I would like to thank my students, Nicole, who actually was working on the molecular wires. She defended a couple of years ago, and actually she started her PhD actually this month in Germany. Fanny, who is an actual student, she's working on the fluorescent chalcones that are going to be used as corrosion inhibitors, and probably these compounds will be sent to Brazil and to Texas as well. And of course, I would like to thank the University of Costa Rica for the grants and the funding, and my great friend Eduardo Poncio. Okay, thank you for the invitation, And thank you all for your attention, your kind attention, for your time. I'm really sorry for the technical problems that we had at the beginning, but yeah, thank you very much, and I'll be gladly try to answer your questions. Thank you very much.
Muito obrigado, professor Leonardo. Parabéns pela apresentação. Yo tengo un par de preguntas. Química orgánica no es mi área, entonces mis preguntas son un poco más generales. Tenemos también algunas preguntas del público que ya nos escribieron en el chat. La primera pregunta, que puede ser que me perdí un poco en la introducción, pero yo quería que hicieras una comparación entre los DES y los líquidos iónicos a temperatura ambiente. ¿Cuáles serían las ventajas de una, ventajas del otro? ¿Cuáles son las ventajas que tenés con respecto a uno o a otro?
Okay, in English.
Yeah.
Okay, yeah. Actually, I didn't want to talk about ionic liquids. I know that probably Ayrton Dupont, it's angry with me. Yeah, I had the opportunity of meeting Ayrton a couple of years ago, and back then it was like the revolution of ionic liquids. And yeah, of course, they have a lot of interesting characteristics. All right, and actually some of them are similar. All right, a lot of the advantages that I presented for DOS are similar. Low volatility, non-flammability, blah blah blah. They're very, very similar. All right. The thing is that well, we don't know exactly how they behave when they're going to degrade. All right, because they are made of kind of a strange cations and strange anions, where there are organic anions and organic cations as well, and inorganic and organic, whatever their mixtures and all this stuff. And the thing is that the problem with them is, one, we don't know how they're going to behave when degrading in nature, and the other thing is that they are so stable that actually degradation is going to take very long time. Okay, in the case of DOS, you have like similar properties, but the thing is that if they're composed of urea is going to degrade in a couple of hours. Okay, choline chloride is also going to degrade in a couple of hours, even whatever days or something. All right, so we have that advantage that we know how they're going to evolve whenever they're gonna get in contact with nature. That's actually the explanation that people is using in order to give a justification of their application. But that's it. Yeah. And the other thing is because there are more possible combinations whenever you want to think of finding a mixture that will form you an eutectic system. All right. And in the case of ionic liquids, well, that you have to search for some kinds of anions, some kind of cations, but you have to do a lot of work to prepare them. You have to do a lot of synthesis in order to prepare them. In here, you already have two compounds. You mix them, and that's it. That's the thing. It's really, really easy to do it. All right. So the synthesis is just simple. All right.
Thank you very much. La otra pregunta al respecto de reciclar. El último tópico que hablaste era sobre reciclar.
Sí.
Además, cuando vos haces una síntesis, si vos querés hacer la misma síntesis, mi pregunta es, ¿podés usarlo más de una vez sin tener que hacer un reciclado del DES? O sea, hiciste una síntesis y podés separar el producto y podés hacer otra batelada de síntesis. ¿O lo usás una sola vez?
Okay. That's a good question. And actually, that's kind of tricky. Depending on what you're doing. For example, if you're doing the same reaction several times with the same conditions, for example, you want to make 100 grams of a product, and you can only make it because you have small equipment. You can only make it in a small scale. All right, you can reuse it. There's no problem because the the reaction system is always going to be the same. Okay, and we do that here, all right, because if it's just the same thing, you're only going to be adding like the same reactants and the same reagents, and that's it, because you're going to expect the same product. But if you're doing catalysis and you do that, you're never going to know what's going on in the reaction. All right, so that's the thing. That's why I also try to meant when I said, well, you gotta think critically and to see if it's worth it or not. Because sometimes it's just easy. Well, I'm going to repeat the reaction. Well, go ahead, do it again, and that's it, right? But if you're doing stuff like catalysis, and then you're just trying to find out if your catalyst is working, and then you use a used solvent, you don't know if it's working because of the whatever is remaining inside or not. You know, so that's it. Try to develop a little bit of critical thinking on the subject.
Ok. Hay un par más de preguntas que te vamos a colocar aquí.
Sí, tenemos tiempo. I missed one point, but is there a difference when changing from a low scale to high scale chemical procedure using DOS? Yes. Well, actually, the thing is, well, your limitations are going to be your equipment, all right? And the other thing is that whenever you're going to scale up your synthesis, all right, remember that if you're using urea as your starting material, urea, you can get it only as an hydrated complex, all right, because it's hydrated urea that you get from commercially available, all right. So the bigger you get, the higher amount of energy you're gonna use in order to get your solvent anhydrous at the beginning in the synthesis, all right. So in our case, what we do is we prepare small batches of solvent, just 1 liter, 1 kilogram of per shot, all right, and then we just dry it up. Okay, that's easy because we only have like a lab scale equipment. Okay, if we were like probably in a higher production facility, we might be able to produce more. But that's the only thing you need to think about. How big is your equipment? And that's all right? Because most of these reactions, they're going to be taking place at either at low temperature or at not so high temperature. So you don't have, that's it. That's the only thing to wait about your equipment limitations.
Ok, obrigado. Temos mais uma pergunta.
Yes. Okay. I actually, the thing is that when these reactions taking place, all right, in DOS, actually we have tested not only with Relin, but we tested with some others. The thing is that when you use the DOS, actually your carbonyl compound is going to be coordinated with urea, okay, through hydrogen bonding, all right, and that also is going to activate the carbonyl, all right, in one hand, and because there's not a lot of solvation inside the reaction, so the hydroxide ions are going to be really close to their acidic counterpart, so reagents are really closed, all right, so reactions takes place really faster, all right. That's the thing, you know. You don't have a lot of solvation. Actually, you don't have solvation. That's kind of my hypothesis as well, all right, because actually it's a huge increase in reaction rate, all right. So instead of 48 hours, 24 hours, you're only getting 3 hours of reaction time. But that's it. Probably that's it, all right. The thing is that you're activating the carbonyl by hydrogen bonding, and because there's no solvation, reactants are closer, and so reaction takes place faster. That's it.
Muito obrigado, professor Leonardo. Muito obrigado a todos que estiveram presentes e a quem assistir a palestra depois. Foi um prazer e foi uma honra tê-lo com a gente apresentando um seminário, e espero que a gente possa se ver em um relativo tempo curto de tempo. Então, obrigado a todos e até a próxima palestra.